Okay, let's go through this study guide for the quarter 3 Chem 1-2 quarter test. So when we're formula writing, if it's ionic, I like to write the ions out first with their charges and then go from there. So in this case, I have Ba2 plus, that's barium. Sulfate is SO4 2 minus. So 2 plus 2 minus, perfectly balanced, BaSO4. No parentheses around that because there's only one sulfate. Ammonium chloride. Ammonium is NH4 with a charge of plus. Chloride is Cl with a charge of minus, giving us NH4Cl. Again, no parentheses. Chlorine monoxide. So that's going to be covalent or a molecular compound. No charges, no crisscrossing, none of that. Anytime you see those Greek prefixes, you just write it as is. Chlorine is just one Cl. Monoxide is 1O, giving us ClO. Silicon tetrachloride, I recognize tetra as a Greek prefix, so this is just going to be SiCl4. Magnesium fluoride, so magnesium is Mg2+, fluoride is F-, crisscross those, getting MgF2. Sodium oxide, Na+, O2-, Na2O. Copper 1 iodide, what does that 1 tell us? Well, it's not necessarily the number of coppers, it's not necessarily the number of iodides, it's the charge of the copper. So we have Cu with a charge of plus, I with a charge of minus, so this ends up being Cui. So it ended up being the number of coppers and the number of iodides, but it doesn't always mean that. It's the charge of the metal. Zinc sulfide, zinc is Zn2+, sulfide is S2-, not to be confused with sulfate or sulfite. So this is just ZnS. Make sure you didn't accidentally keep the 2's there and say Zn2S2. You got to simplify it down. Potassium carbonate, that's K+ is potassium, CO3 2-, so it's going to be K2CO3. Lead 2 acetate. So we have Pb with a 2+ charge. Acetate is C2H3O2 with a minus charge. Now we're going to need 2 acetates and 1 lead. So it's going to be Pb parentheses C2H3O2 close parentheses 2. So you need parentheses when you have more than one of the polyatomic ion. No parentheses when you have one of them, like in K2CO3, we have 1 carbonate. All right, iron 3 hydroxide. So iron is Fe, and in this case, it has a charge of 3+. Hydroxide is OH-, so we need Fe parentheses OH close parentheses 3. People often forget parentheses with hydroxide. I'm not sure why, but make sure you have parentheses. If you just say FeOH3, that's wrong. Silicon dioxide is going to be SiO2. Nitrogen trifluoride, NF3. Again, anytime you see any Greek prefixes, don't think about charges, don't think about crisscrossing, you just use the Greek prefixes. Chromium 3 oxide, that's Cr with a 3+ charge, O with a 2- charge, giving you Cr2O3. Calcium chlorate. Calcium is Ca2+, chlorate is ClO3 with a charge of minus, giving us Ca parentheses ClO3 close parentheses 2. Cobalt 3 nitrate. It's CO with a charge of 3+, NO3 with a charge of minus, giving us CO parentheses NO3 close parentheses 3. Ammonium phosphate. Ammonium is NH4 with a charge of plus. Phosphate is PO4 with a charge of 3-. So we're going to need 3 of those ammoniums, so parentheses around those, NH4 close parentheses 3, and 1 phosphate, PO4, just like that. All right, on to the other side where we're writing formulas, names. So CuSO4, looks like there's a 0 there instead of an O, but it should be CuSO4. Now, Cu is copper, SO4 is sulfate. We can't just say copper sulfate though, because copper is a transition metal. So we need to figure out the charge of this particular copper. How do we know that? Well, it's bonded to 1 sulfate. We have 1 copper bonded to 1 sulfate and they're balanced. So what must that copper's charge be? Well, since sulfate is 2-, that copper must be 2+, So that's going to be copper, Roman numeral 2, sulfate. PCl3, that's going to be covalent because it's nonmetal bonded to nonmetal. So we're going to use Greek prefixes. Phosphorus, trichloride. Okay, note that we don't use mono for the first one if there's one of them. Mono only gets applied to the second one if there's one of them. Li3N, lithium's a metal, nitrogen's a nonmetal, so this is going to be simply lithium nitride. Okay, and no Roman numerals because lithium's a type 1 metal. It has a known consistent charge. BaSO3, just like above, barium is a type 1 metal. Sulfite is a polyatomic ion, barium sulfite. N2F4, N is a nonmetal, F is a nonmetal. This is going to be covalent, so we use Greek prefixes. Dinitrogen, tetrafluoride. And make sure you spell that correctly, Fluoride. KClO4, K is potassium. ClO4 is perchlorate. Potassium perchlorate. NaH, we don't see H too much in here. H can either act as a positive or as a negative. And in this case, we know it's negative because it's on the opposite end of a sodium. Sodium is positive, so in this case, hydrogen is negative. So in this case, we're going to call this sodium hydride. Hydride, because it's the anion version of hydrogen. HNO2. So here, hydrogen's acting as a cation. It's the front part of this. So we're going to call it hydrogen nitrite. Now, you will later learn when we do acids and bases, this is called nitrous acid. But for now, hydrogen nitrite. Next one, Sr3P2. So strontium is a type 1 metal. So we just say strontium. P is phosphide. Not phosphate, not phosphite, but phosphide. MgOH2, that's just going to be magnesium hydroxide. Al2S3, that's going to be aluminum, I probably spelled that wrong there, sulfide, not sulfate, not sulfite, but sulfide. AgBr, that's just going to be silver bromide. Even though silver is kind of smack dab in the middle of the transition metals, you're not going to use Roman numerals for this because it has a known consistent charge. It's part of what I call the 3-2-1 rule, from aluminum down to the left. It's 3 plus 2 plus plus. Silver is always plus. P4O10, that's going to be tetraphosphorus decaoxide, but instead of saying decaoxide, you cut the A out and just say decoxide. Tetraphosphorus is decoxide. Okay, H followed by acetate. So we're going to call this hydrogen acetate. We'll later learn that's called acetic acid when it's aqueous, but don't worry about that for now. Next is calcium iodide. MnO2, that's going to be manganese, which is a transition metal. Now, we can't just say manganese oxide because, well, like I said, it's a transition metal. So we need to figure out the charge. So we have 1 manganese and 2 oxygens. Well, each oxygen is 2 minus. So what must this manganese be? Well, it must be a 4 plus in order to balance it out. So we're going to call this manganese, Roman numeral 4, oxide. Now, note that this does have a common name. It's sometimes called manganese dioxide. That's just an old kind of name that's stuck with it. You've used this before. This is the black powder that serves as the catalyst for hydrogen peroxide. It's that stuff you added that causes the hydrogen peroxide to fizz. And it's called manganese dioxide on the bottle. That's kind of an old name. The official name is manganese 4 oxide. Li2O, that's going to be lithium oxide. FeI3, that's iron, and you have to figure out its charge. Well, since this iron is bonded to 3 iodides, it must have a 3 plus charge, so we say iron 3 iodide. Cu3PO4. Let's break this one down. So we have 3 coppers and 1 phosphate, PO4 minus. Well, in order for this to be balanced, what must each of these coppers charge be? Well, it must be 1 plus or just plus. So the charge of copper is 1 plus. So we're going to say copper, Roman numeral 1, phosphate. Okay. PCl3, that's going to be phosphorus trichloride. And remember, no mono if it's just the first one that's alone. All right, a few more. CS3N. CS is cesium. It's a type 1 metal. So we just say cesium nitride. Next one is going to be zinc nitrate. Zinc is a type 1 metal. We know it's charged, so you don't say zinc 2. N2O, that's going to be dinitrogen. And then monooxide gets shortened to monoxide. And the last one, we have HF. So H is a nonmetal, F is a nonmetal. So we're going to call this one hydrogen monofluoride. Now, this one could be arguably considered ionic. When we get to later in the year, you might see the electronegativity difference, calling it ionic. So you could actually call this hydrogen fluoride. It's kind of ambiguous. When this is dissolved in water, it'll be called hydrofluoric acid. So let's not get too hung up on whether this one is hydrogen monofluoride or hydrogen fluoride for now. Okay, on to the next part. So here we have a series of equations. So what the instructions tell you is write the balanced equations out, including state symbols when appropriate. And if it's a double replacement reaction, also include the net ionic equation. Now that really only applies to double replacements. So this one, oh, and identify the type of reaction for each one. So here we have ammonium sulfate. So ammonium is NH4 plus. Sulfate is SO4 minus, so this is going to be NH4 SO4. Reacts with barium nitrate is BaNO3. Now this one doesn't indicate states, but 99% of the time when you have a double replacement like this, it's going to be solutions of, it's going to be aqueous. In fact, even if these are supposed to react, if you just take the solids and kind of fling the solids together, nothing's going to happen. They really need to be dissolved in water so the ions can move. Okay, so this is a double replacement because we have 4 ions. So we're going to switch partners. So ammonium bonds with nitrate, giving us NH4NO3. You look that up on your solubility table. That will be aqueous. Barium sulfate is BaSO4. That is going to be solid. So this one does take place. And we balance it with just a 2 right there. So our type of reaction is a double replacement reaction or double displacement reaction. And since this is a double, let's write the net ionic equation as well. So the net ionic equation is just the ions that actually form your precipitate. So my precipitate is barium sulfate. So the ions that formed it are my barium ion, which is Ba2 plus aqueous, plus my sulfate, SO4 minus aqueous, yields my BaSO4 solid. Those are the only ions involved in the net ionic equation. The other ions, being ammonium and nitrate, are spectator ions because they start out aqueous and they end up aqueous. They don't actually do anything. Okay, zinc metal is added to a solution of copper 2 chloride. So zinc is Zn, that's going to be solid, added to a copper 2 chloride solution, CuCl2 aqueous. This is going to be a single replacement reaction. In single replacements, I say you either have metals replacing metals or hydrogen is mixed in there. So maybe a metal replacing hydrogen or hydrogen replacing a metal. Or you're going to have halogens replacing halogens. In this case, the zinc is by itself. That's a metal, so it's going to replace the other metal, or at least it's going to attempt to. So for single replacements, you got to check your activity series. The one that's by itself needs to be above the one it's trying to replace, or else it will not, and it'll be no reaction. Zinc is above copper, so this will occur. So the zinc bumps the copper out, giving us zinc chloride. Now zinc is 2 plus, chloride is 1 minus, so this is ZnCl2. Now notice, in this case, you happened to literally swap it out, but that it just happened to be that way because the copper and the zinc have the same charges. The copper gets bumped, so we say plus Cu, that's going to be solid. It looks like we're already balanced here. So yeah, nothing else to add. Single replacement reaction, balanced equation. Propane gas, C3H8, I tell you it's a gas, burned in excess oxygen. So plus O2, because oxygen is a diatomic element, which I call a Brinkelhoff. You may hear me say that term. That's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, Brinkelhoff. So this is combustion. You just got to memorize what happens in combustion. You have a hydrocarbon, which is a CH-based fuel, could be O in there as well, plus O2 yields CO2 plus H2O. Okay, to balance this, I always start with my H's. I go H, then C, then O. For my H's, I have 8 here and 2 here, so I'll put a 4, and that's fine because it's even. Carbon, I have 3 here, so I'll put a 3 there. And now I'm just going to add up my O's on the right and balance it on the left. So 3 O2s is 6 oxygens. 4 O's is 4 oxygens. 4 and 6 is 10. So I'm going to put a 5 right there. Okay. Number 4, magnesium and nitrogen gas are heated together. So magnesium is just Mg. That's going to be a solid. Nitrogen gas is N2 gas. Now, why is Mg just Mg, whereas N is N2? Diatomics. You got to be familiar with those 7 diatomics, H, NOF, Cl, Bri. So those always pair up when they're alone. Magnesium's not, so it just goes like this. All right, what type of reaction? Well, we have 2 lone elements, so the only thing they can do is come together in a synthesis or combination reaction. All right, so we're going to form magnesium nitride. You're not just going to blindly smush these and say MgN2. You're going to say, well, magnesium nitride, which is going to be Mg with a 2 plus, bonding with N3 minus, crisscross, giving you Mg3N2, which we then balance with a 3 right there. All right, synthesis reaction. Chlorine gas. Chlorine is a diatomic element, so I'm going to say Cl2 gas, is bubbled through a solution of sodium bromide, NaBr. Solution of means aqueous. All right, we're looking at a single replacement reaction or single displacement reaction. The element that's by itself, I call it the bully. It's going to try to bump something out, is chlorine. Chlorine is a halogen, and halogens try to replace other halogens. So on our chart here, we're going to look at the bottom section and ask ourselves, can chlorine replace bromine? And the answer is yes, it can. So this reaction will proceed. If you ever find yourself comparing something down here to something up here, you're doing it wrong, okay? Chlorine will not attempt to replace sodium. It doesn't make any sense. All right, so the chlorine bumps out the bromine. We end up getting sodium chloride, and bromine gets bumped. Is bromine one of those diatomics? Yes, it is. So we say Br2. And Br2 is one of our rare liquids at room temperature. And we just balance this out now with a 2 there and a 2 there. Solutions of, now I can already tell that's going to be a double replacement reaction because we have 2 solutions of ionic compounds. So lead nitrate, ooh, we need a charge there, whoops. Let's assume that this is lead 2. Probably should have edited that in. Let's assume that's lead 2. That's usually what lead is. All right, so Pb 2 plus and NO3 minus is going to be Pb parentheses NO3 2. Solutions of means aqueous. Calcium iodide is going to be CaI2. Let's assume that's also aqueous. Lead iodide is it's going to be lead 2 iodide, assuming this 2 carries over. So it's going to be PbI2, which is solid. Calcium nitrates are other compounds, Ca parentheses NO3 2, and that is going to be aqueous. And this ends up being balanced already yet again, this is a double replacement reaction. And because it's a double replacement, let's write the net ionic equation here. So my precipitate is the lead-2 iodide. So this came from one lead, which is Pb2 plus aqueous, plus 2 iodide ions, which is I minus aqueous, yields PbI2 solid. Okay, now the most common mistake we see is people will leave the I2 together as I2, citing the fact that it's a diatomic. That doesn't apply when it's aqueous, meaning it's dissolved as an ion. It splits into individual iodide ions. Okay, moving on. Number 7, sulfuric acid, H2SO4 aqueous, is combined with sodium hydroxide, NaOH. And that's probably going to be aqueous. It doesn't indicate it there, but I'll put the aqueous. So what type of reaction? Well, technically this is a double replacement reaction, but it also has a special name, which is acid-base, B-A-S-E, neutralization. Neutralization. Because H2SO4 is an acid, it starts with hydrogen, and NaOH is a base, it ends in hydroxide. So it's just a special type of double replacement. Let me shift that down a little bit. Okay, so the hydrogen from the acid bonds with the hydroxide from the base, giving us HOH or H2O, and that is liquid. The sodium bonds with the sulfate, giving us Na2SO4, which is aqueous. And we balance this with just a 2 there and a 2 there. Okay, now since this is technically a double replacement, we can write a net ionic equation. Now we didn't form a solid, but we did form a liquid, and we can say how we formed that. So we had H plus aqueous plus OH minus aqueous formed H2O liquid. That's what really happened here. Number 8, isopropyl alcohol, C3H8O, is burned in oxygen, O2 gas. All right, you got to recognize that this is a combustion reaction. How do you know it's combustion and not like single replacement? Because the thing here, my first product, is clearly a hydrocarbon. It's a CH molecule that, in this case, it has a little bit of oxygen as well, but that is a hydrocarbon. So we're going to form CO2 and H2O. Okay, let's go with our H's first. So I have 8 H's and 2 H's, so 4. Carbons, I have 3 here and 1 here, so 3. Let me add up my O's. 2 times 3 is 6. It sounds familiar. 4, so I need 10. So I'm thinking of just putting a 5 here and being done, but oh, wait a minute. We have this extra O here. Well, sometimes I say, when in doubt, double everything for combustions. So instead of 1, 3, 4, I'm going to go 2, 6, 8. Now, I just want to make sure my H's and C's should still be balanced. For H's, I have 2 times 8 is 16. 8 times 2 is 16. 2 times 3 is 6. 6 times 1 is 6, so we're good there. Now let's count our O's. On the right side, I have 6 times 2 is 12. 8 times 1 is 8. Add them together, I get 20. On the left side, I'm going to account for 2 of them here, meaning I need 18 more. So I'm going to put a 9 there and be done. 2, 9, 6, 8. Combustion reaction. Iron metal shavings are added to hydrochloric acid. And I think for this one, I said, assume the iron forms, I guess, I don't have it in front of me. 2 plus probably is what I would have assumed. If I said 3 plus, it'll be different on the answer key. Okay, so iron is Fe, solid, is added to hydrochloric acid, HCl aqueous. So what type of reaction here? Single replacement reaction, because we have one element plus a compound. What's going to try to replace what here? Remember, I say metals replace metals, halogens replace halogens. But that one exception to that first one is that metals will replace hydrogen as if it's a metal. And that's exactly what's going to happen here. Iron is going to attempt to replace hydrogen. And according to the activity series, iron is able to do so. So we're going to end up with iron chloride. Now here's where that extra information is. I'm going to assume that it forms a 2+ ion, giving us FeCl2. Hydrogen gets bumped out. Hydrogen is a diatomic element, so I say H2. We balance this with a 2 there, and it looks like we're good. If I did say 3+, it'll give you FeCl3, and then you would just need to balance it with 2s and 3s in your coefficients. Okay. I think this is the last one. Sodium metal, that's Na solid, is added to distilled water, so that's just H2O liquid. Now this requires a little bit of background knowledge from the lab we did. Remember we took calcium and added water and those big fizzes? Well, when a metal reacts with water, it is a single replacement reaction, but the metal doesn't replace hydrogen and bond with oxygen like you might think. It replaces some of the hydrogen and bonds with hydroxide. So basically when a metal bonds with water, you get a metal hydroxide plus hydrogen gas. So in this case, we're going to form sodium hydroxide. And some of the H still gets bumped, giving us H2 gas. We put a 2 there, and a 2 there, and a 2 there. Let me just confirm. 2 NAs, 4 H's, 2 O's, and we're good. Okay, let's move on. All right, so the stoichiometry section started with mass percent or percent composition. We're probably not going to see much of an emphasis on this. This is really just like getting used to molar masses, really. So percent nitrogen in each of the following. So NO, the first step to finding this is finding the molar mass of NO. So N is 14.01, O is 16.00, so the molar mass is 30.01. So to find the percentage N, it's going to be 14.01 grams divided by 30.01 grams times 100 gives us 46.68% N. And I'm being consistent with myself for sig figs. I have 4 sig figs here, 4 sig figs here, so I'm going to give myself 4 sig figs there. All right, for the next one, NO2, so the molar mass is 14.01 plus 2 times 16, which is 32.00. So the molar mass is 46.01 grams. There's still one N, so I'm going to say 14.01 grams divided by that times 100 gives us 30.45% N. Part C, N2O4, so the molar mass here is going to be 28.02, that's 2 N's, plus 64, that's 4 O's, is 92.02 grams. And I have 2 N's in there, so I'm going to say 28.02 grams divided by that. And that gives me 30.45 percent N. And notice that's the same as back here, and that makes sense because NO2 is actually the empirical formula of N2O4. So it makes sense that the percent composition is going to be identical. Lastly, N2O, the molar mass here is going to be 2 N's, so 14.01 times 2, plus 1 O, 16, is 44.02 grams per mole. We take 2 N's, which is 28.02, and divide that, multiply by 100, 63.65%. All right, so that's really just like practicing your molar masses. All right, on to some real stoic problems. Calcium carbonate decomposes upon heating. So this is decomposition. So CaCO3 breaks down into calcium oxide is CaO and carbon dioxide, CO2. I'll tell you that's a gas there. Part A, write a balanced equation. Hey, look, it's already balanced. Nice and easy. Part B, how many grams of calcium oxide will be produced after 12.25 grams of calcium carbonate is completely decomposed? So this is a classic grams to grams stoic problem, or grams in, grams out. I like to rewrite my coefficients underneath, 1, 1, 1. So we start by taking the grams in the problem, turning it into moles. 12.25 grams of CaCO3 We're going to multiply that by 1 mole over the molar mass, or in other words, just divide that by molar mass. So 40.08 is carbon plus 12.01, 40.08 is calcium, 12.01 is carbon, and we add 3 O's, which is 48, gives us 100.09 grams. 12.25 divided by this, 12.25 over 100.09 gives us 0.1224 moles of CaCO3. I'm going to put that right underneath here for organization. So that's my moles of calcium carbonate. And we're looking for how many grams of calcium oxide. That's right here. So now we apply our mole ratio. Notice the mole ratio is 1 to 1. So X is going to be the exact same number. It's 0.1224 moles of CaO because it's a 1 to 1 mole ratio. And now we're going to find grams of that by multiplying by the molar mass, not the same molar mass, but now it's the molar mass of CaO, which is 40.08 plus 16.00. So multiply that by 56.08 grams per mole, which will give us, with 4 sig figs, because my problem gave us 4, final answer of 6.864 grams of CaO. Okay. Question 4. Hydrogen gas and bromine react to form hydrogen bromide gas. Okay. So we're doing a balanced equation. We're doing, this is going to be a limiting reactant problem. I can tell because we're given the mass of hydrogen and the mass of bromine. Anytime you're given both amounts of reactants, you have to find the limiting reactant. In fact, I straight up asked that right here. Part C, how many grams of hydrogen bromide can be produced using that? And part D, how many grams of the excess is left unreacted? So we're asking quite a lot about this, including mass of excess that's unreacted. I would say this justifies us starting a BCA table. Maybe not even finishing the BCA table, but at least starting it. So I'm going to start with my balanced equation. Hydrogen gas is H2 gas, plus bromine is Br2 gas. These are both diatomics, and they're going to form hydrogen bromide, which is this HBr, because it's +1 and -1, and that's a gas as well. For balancing, we need a 2 there, which gives us a 1 to 1 to 2 mole ratio. Okay, BCA table. B stands for before, C stands for change, A stands for after. So before the reaction occurs, we're going to turn grams and grams into moles and moles. So 3.2 grams of hydrogen, that's H2, not H, H2. We're going to divide that by the molar mass of H2, which is 2.02. 3.2 over 2.02 gives us 1.58. And that's moles. So that is how much I have before, 1.58. In fact, I'm going to do a color change here. Let's go black. 1.58 moles. How about the Br2? I have 9.5 grams of bromine, Br2. We're going to multiply that by 1 mole over Br2. 79.904 times 2 is 159.81. 9.5 divided by this gives us 0.0594. 0.0594 moles. Okay. How much HBr do we have before the reaction begins? None, because the reaction hasn't started, so we put a 0 there. All right. Now we have to identify the limiting reagent or limiting reactant. So there's several ways of doing this. You can just kind of look at the ratios and kind of work out how much you would need, or you can take each of these moles divided by the coefficient and see what's smaller. In this case, it's really easy to see because it's a 1-to-1 ratio, so simply the smaller number of moles is going to be your LR. And in this case, it's not even close. I mean, look at that. So clearly the Br2 is going to run out first because there's nothing compared to the H2. So that's my LR, limiting reactant, and that's my ER, excess reactant. So part A is done, part B is done. Let's complete our BCA table. That'll help us with C and D. So the next step in the BCA table is the change, which is how much is going to be depleted on the reactant side and produced on the product side. So we start with the limiting reagent or limiting reactant, and all of that's going to disappear because it's limiting. It, by definition, it all goes away and it stops your reaction. That's why we say the reaction is limited to how much you have. So we're going to say minus 0.0594, leaving us with 0 moles after. Part C says how much of this can be produced. So let's figure this part out right now. Well, look at the mole ratio. It's 1 to 2. So for every mole of bromine that got consumed, 2 moles of HBr are going to get produced. So 0.0594 times 2 is 0.119, and that's getting produced on this side, 0.119 moles. And since we started with 0, we added 0.119. After the reaction, we have 0.119, and again, that's the moles. Let's finish this part C out before we finish the BCA table. That's my moles of HBr. We're going to multiply this by, and run out of room here, by the molar mass of HBr, which is 1.01 plus 79.904 times 80.91, giving us a mass of, with 2 sig figs, 9.6 grams. That is part C. 9.6 grams of product gets produced. Part D, how many grams of the excess reactant is left unreacted? So we're finishing our BCA table here. Well, is 1.58 moles going to react? No, that's the excess reactant. That's more than we need. In fact, it's a lot more than we need. Well, how much is actually going to react? Well, if 0.0594 moles of my LR reacted, 0.0594 moles of the ER are going to react, in this case, because it's a 1-to-1 ratio. So now we do the subtraction. 1.58 minus 0.0594 gives us, and I want to be very precise here, decimal places. I have 2 decimal places up top, 4 decimal places here. I'm going to limit this to 2 decimal places, and I'm going to call it 1.52 moles remain. So my BCA table is complete. All the numbers you see in black there are in moles. And this is going to help us answer part D, which is how many grams of the excess remain. So this is moles. We're going to multiply this by 2.02, which is the molar mass of H2, which gives us 3.1 grams of H2 remain. Okay? 3.1 grams, which is almost as much as we had. Notice we started with 3.2, we end with 3.1 remaining, and that's because the molar mass is so small compared to bromine. All right, one more problem. When ammonia gas, now I think I highlighted on the other part, ammonia is NH3. It's very similar to ammonium, which is NH4+. In fact, ammonium is just ammonia that gains an H+. So NH3 gas, oxygen gas, which is O2, and methane gas, which is CH4. When these are combined, the products are hydrogen cyanide gas, which is HCN gas. Oh, not HCl, HCN. And water. Very rarely do we have a 5-compound problem, but that's what we have here. All right, balanced equation. Where do we start? It's gonna be a lot of trial and error, I think. Okay, so what needs balancing? Looks like my N's are okay. My H's, I see 7 of them on the left and 3 on the right. Let me try, I'm going to start with a 2 here just to get me out of odd territory. I'm going to put a 2 there. By putting a 2 there, I need to put a 2 here to fix my n's. And I need to put a 2 here to fix my c's. So my n's are good, my c's are good. Let's look at my o's. No, I want to fix my h's. See what I need to do to fix the h's. So I have 2 h3s is 6 h's. 2 h4s is 8. 6 and 4 is 6 and 8 is 14. So I have 14 h's on this side right now. On this side, I have 2 h's. I don't want to touch this number. I want to keep that as a 2 because if I mess that up, it's going to change my h, my c's and my n. So I'm going to leave that as 2, meaning I need 12 here. How do I get 12? Let me put a 6 there. And by putting a 6 there, that gives me 6 O's. So I can put a 3 there, and I think I'm good. Let's double check because this is really tricky. 2 n's, 2 n's. 2 times 3 is 6 h's, plus 2 times 4 is 8 h's. 6 and 8 is 14 h's. Here I have 2 h's plus 12 h's, 14, okay? And then O's, I have 6 and 6. Yeah, oof, that's a challenge. 2, 3, 2, 2, 6. Balanced equation is done. Part B, calculate the mass of each product produced. Remember, products are on the right side, so I'm looking for this and this. When 225 grams of oxygen gas react to an excess of the other 2 reactants. So 225 grams of oxygen gas, which is O2, not O, O2. So we turn this into moles using 32.00 grams, not 16, 32. So 225 over 32 is 7.03 moles of O2. 7.03 moles. Okay, and now we just apply our mole ratios. Now I always look for the path of least resistance, and for me, if I'm solving for either this first x or that second x, I'm going to solve for that second one first, because a 3-to-6 ratio is easier than a 3-to-2 ratio. Yeah, similar. 3 to 6, that's twice as much, so I'm going to double this. 7.03 times 2 is going to be 14.06. I'll trim down the sig figs afterwards. So that's my moles of H2O. I'm going to multiply that by the molar mass of H2O, which I happen to have memorized because water is very common. So 14.06 times 18.02 is 253 grams of water. Now that I have this, I can use that to easily solve for this one, because a 6-to-2 ratio just means it's going to be 3 times less. Not 3 times less mass, but 3 times fewer moles. So 6-to-2, I have 14.06 moles. I'm going to divide that by 3 to give us 4.69 moles. 4.69 moles of HCN. By the way, I could have easily found that by just applying a 3-to-2 ratio from the 7.03, which would mean dividing by 1.5. In fact, I'll double check. 7.03 divided by 1.5 gives me the exact same number. Okay, 4.69 moles of HCN. Let's convert that to moles by multiplying by molar mass. So 1.01 is H plus 12.01 plus 14.01 gives me 27.03 is a molar mass. Multiply that by 4.69, giving me a final answer of 127 grams of HCN. Okay, so part B is done. Part C, the actual yield of the experiment, I would call that the experimental yield, is 105 grams of HCN. Calculate the percent yield. So percent yield is going to be the experimental yield, which in this case is 105 grams. We divide that by the theoretical, which is 127. Multiply that by 100 and keep our sig figs consistent. 82.7% yield. Okay, and I believe that's everything. All right, well, good luck on your quarter test. Don't forget there's extra help sessions throughout the week, and you could always ask your chem teacher if you need any extra reinforcement. Good luck, everyone.